This is Bayes' theorem. It is called so after Reverend Thomas Bayes, an 18th century English mathematician and Presbyterian minister, who first formulated it in an essay towards solving a problem in the doctrine of chances. As it always happens in these cases, the original essay is much more complicated than the theorem. Bayes' theorem is simple. H is a hypothesis, any statement about which we are interested to know whether it is true or false. E is the evidence that we use to answer that question. P stands for probability, a number that goes from 0, which means complete impossibility, there is no way that the hypothesis is true, it is certainly false, to 1, the hypothesis is certainly true, there is no way that it is false. And this vertical bar is the sign for conditional probability, which simply means the probability of something given something else. So this is the probability of the hypothesis we are considering, given or in the light of the evidence associated with it. Probability theory is a branch of mathematics that started properly in the 17th century. But probability itself is a very basic concept. When a primitive hunter went out in search for food, he had an idea of the probability that he would find it, and an idea of the probability of himself ending up being the food for some other animal predator. He formed those probabilities in the light of his own experience, as well as the experience of others that was communicated to him. Another example, when a baby throws a ball in the air, he has initially no idea where it will end up. It is through the evidence accumulated by repeated observation that he learns that the ball lands on the floor and does not, for example, float in mid-air or ends up in another room or flies out of the window. So from the very start, we evaluate hypotheses in the light of some evidence. The Bayes theorem says that the probability of the hypothesis, given the evidence, is equal to the probability of the evidence, given the hypothesis, times the probability of the hypothesis, divided by the probability of the evidence. At start, this seems confusing, but it's very simple. First of all, let's see why it must be true. This is the probability of H times E. That is the probability of H and E being both true at the same time. As with ordinary multiplication, the order doesn't matter, so the probability of H times E is equal to the probability of E times H. This is the definition of conditional probability. The probability of H given E is equal to the probability of H times E divided by the probability of E. In the same way, the probability of E given H is equal to the probability of E times H divided by the probability of H. I put them this way to show that since the terms on the left are equal, so must be the terms on the right. But this is none other than the Bayes theorem. To repeat, the probability of the hypothesis, given the evidence, is equal to the probability of the evidence given the hypothesis times the probability of the hypothesis divided by the probability of the evidence. So you can just imagine Reverend Bayes looking at the formula and saying, is that all there is to it? Well, yes, Minister, that's all, but there is so much in it. Let's see. So first of all, how do we go about calculating it? What we need to do is expand in the denominator, the probability of E. By definition of conditional probability, The probability of E is equal to the probability of E given H times the probability of H plus the probability of E given not H times the probability of not H. Remember that the hypothesis H can either be true or false. When it is false, we say that not H is true, where the probability of not H must be equal to 1 minus the probability of H. For example, if the probability that H is true is 70%, the probability that it is false is 30%. By replacing the probability of E, we get this apparently troubling formula, which however simply says that the probability of H given E depends on three things. The probability of E given H, which appears here and here, the probability of H, which appears here, here, and here, and the probability of E given not H, which appears here. Let's take an example. Let's say that we are evaluating the probability of fire, and we do it on the basis that we can see evidence of smoke. So in this 2 by 2 matrix, the hypothesis can either be true, there is fire, or false, there is no fire, and the evidence can either be positive, there is smoke, or a negative, there is no smoke. There are 4 possibilities. The evidence is positive and the hypothesis is true, there is smoke and there is fire, therefore we call this a true positive. There is smoke but there is no fire, a false positive. There is no smoke and no fire, a true negative. And there is no smoke but there is fire, a false negative. So the evidence of smoke can give 2 right responses, true positives and true negatives on the first diagonal, and 2 wrong responses, false positives and false negatives on the second diagonal. Let's say we make 200 observations. In 19 of them, there was smoke and fire. In 18, there was smoke but no fire. In 1, there was fire but no smoke. And most of the times, 162 out of 200, there was no smoke and no fire. Typically, we care more about one of the 2 errors. In the case of fire, a false negative, where we see no smoke and miss calling a fire, is much worse than a false positive, where we see smoke and give a false alarm call. In the same way, a hunter who hears rustling in the bush doesn't want to miss the lion coming out of it, even at the cost of fleeing a few times when the rustling was caused by the wind, or worse, by a meaty antelope. So there is a trade-off between the 2 errors. Less of one means more of the other, and vice versa. In the extreme, if we want to avoid missing a fire or a lion at all costs, we can call one every time. This way, we'll certainly never miss them, but of course, we'll generate a lot of false alarms, an unworkable precaution and definitely not a good hunting strategy. So, we need to strike an acceptable balance between the 2. Let's look at these numbers in relative terms. First of all, there was a fire 20 times out of 200 times. We call this the Bayes rate or prior probability, in this case 10%. Then, out of the 20 cases of fire, 19 times it was signaled by smoke. This is the true positive rate, 95%. And 1 time there was a fire with no smoke. This is the dreaded false negative rate, 5% in our case. Out of the 180 cases of no fire, in 162 of them there was no smoke either. This is the true negative rate, 90%. And in 18 of them, smoke gave a false alarm. The false positive rate was 10%. Here are the numbers. The 10% Bayes rate, the true positive rate, and the false negative rate in the case of fire, and the false positive rate and the true negative rate in the case of no fire. Notice, obviously, that the columns must add up to 1. So the false negative rate equals 1 minus the true positive rate, and the true negative rate equals 1 minus the false positive rate. The other thing to notice is that the two error rates are not necessarily equal. Here, for example, one is 10% and the other is 5%. When the error rates happen to be equal, we call this symmetric evidence. In that case, also the rows of the matrix add up to 1, and the false positive rate equals 1 minus the true positive rate. Hence, the variables in the Bayes theorem are reduced from 3 to 2. But in our case, they are 3. The Bayes rate, the prior probability of the hypothesis before the evidence, 10%. The true positive rate, the probability of the evidence given that the hypothesis is true, 95%. And the false positive rate, the probability of the evidence given that the hypothesis is false, 10%. We plug these three numbers in the Bayes formula, and the result is 51.4%. This is the Bayes theorem in our notation. This stands for posterior probability, the probability of the hypothesis after or in the light of the evidence. So we conclude that the evidence of smoke is, as we know, quite a good signal of the presence of fire. Before seeing smoke, the prior probability of fire was 10%. After seeing smoke, the posterior probability goes up to above 50%. How accurate is smoke as a signal for fire? A natural measure of accuracy is the average of the two true rates. This is equal to 1/2 plus half of the gap between the true positive rate and the false positive rate, in our case 92.5%. According to this measure, perfect accuracy occurs when there are no errors. In that case, the false positive rate is 0 and the true positive rate is 1. This gives 100% accuracy. We call this a perfect evidence. Think of the baby throwing the ball. When he does it, the ball always lands on the floor and nowhere else. There are no false positives. And if he does not throw the ball, there is no way that the ball will land on the floor by itself. No false negatives. Perfect evidence is the high road to learning. It demonstrates cause and effect. Children crave perfect evidence. Mine bombard me with what happens if questions, where their implicit assumption is that if it happens that way, that's the way it always happens. Whenever feasible, my answer is let's try, and I make a little experiments for them. Other times, when, say, the question is something like, Dad, what happens if I throw this vase out of the window? They'll have to take my word for it. Of course, we all want perfect evidence, but it's not always there. So we have to learn to get by with imperfect evidence, evidence containing false positives and or false negatives. The opposite of perfect accuracy, perfect inaccuracy, is when the true positive rate equals the false positive rate. In that case, our measure of accuracy is 50%. Think of it as coin toss accuracy. Indeed, the troubling aspect of a perfectly inaccurate signal is that it's not always wrong. If it were, it would be a perfectly accurate contrarian indicator, which occurs if the true positive rate is 0 and the false positive rate is 1. Hence, our measure of accuracy becomes 0. If you prefer a measure of accuracy that is 1 with perfect accuracy, 0 with perfect inaccuracy, and -1 with perfect contrary accuracy, you can use A star, which is equal to TPR minus FPR. So let's go back to our Bayes formula. We can see that with perfect evidence, TPR equals 1 and FPR equals 0, the posterior probability equals 1. Perfect evidence produces certainty. If, on the other hand, TPR equals FPR, the denominator here becomes TPR, and therefore we have that the posterior probability remains equal to the prior probability. Perfect inaccuracy means worthless evidence. But another way to get a posterior probability of 1 is to have BR, the Bayes rate, equals 1. If we start with a prior probability of 1, no amount of evidence, perfect or imperfect, can change our belief. We call this faith. We can have faith in the truth of the hypothesis. If BR equals 1, PP, posterior probability, equals 1, irrespective of TPR and FPR. Or we can have faith in its falsity. If BR equals 0, then PP, posterior probability, equals 0, again irrespective of the other two terms. But the posterior probability can equal 1 or 0 also as a result of evidence. We have seen perfect evidence with where both errors are equal to 0, and we have seen perfect contrary evidence where both the true positive rate and the true negative rates are 0. Think, for example, of the baby testing the hypothesis, I can bounce a crystal ball. But we can have certainty also if either one of the items in our 2x2 matrix is 0. We call this conclusive evidence. For example, if the false positive rate is 0, PP, the posterior probability, is 1, irrespective of BR and TPR. You can see it here. We call this a smoking gun. If the suspect is found with a smoking gun in his hands, he is certainly guilty. There is no way that he could possibly be innocent. The evidence admits no false positives. A smoking gun is conclusive evidence of guilt. Likewise, if the true positive rate is 0, PP, the posterior probability, is 0 irrespective of BR and FPR. We call this a perfect alibi. If the suspect has a perfect alibi, for example, he can demonstrate that he was elsewhere at the time of the crime, he is certainly innocent. There is no way that he could possibly be guilty. The evidence admits no true positives. A perfect alibi is conclusive evidence of innocence. The other two cases of conclusive evidence refer to negative evidence, and they are when the true negative rate is 0, which I call a strangler's stye, and when the false negative rate is 0, which I call a barking dog. You can get the details of it in the Blinded by Evidence paper available on the blog. Notice that conclusive evidence differs from perfect evidence. Finding a smoking gun is conclusive proof of guilt, but if no smoking gun is found, it does not necessarily mean that the suspect is innocent. Likewise, a perfect alibi is conclusive proof of innocence, But not having a perfect alibi does not necessarily mean that the suspect is guilty. To summarize, this is how we can reach the two boundaries of the probability spectrum. We can be sure that the hypothesis is true through faith, perfect evidence, conclusive positive evidence, smoking gun, or conclusive negative evidence, strangler's tie. And we can be sure that the hypothesis is false, again through faith, perfect contrary evidence, conclusive positive evidence, a perfect alibi, and conclusive negative evidence, a barking dog. This means that without faith, perfect or conclusive evidence, we are left somewhere in the middle of the probability spectrum, dealing with imperfect, inconclusive evidence like smoke and fire. A convenient way to look at this is to rewrite Bayes' theorem in odds form. When we do that, the result is that posterior odds, PO, are equal to the ratio of the true positive rate and the false positive rate, known as the likelihood ratio, times prior or base odds. Odds are simply the ratio of a probability by its complement to 1. So, for example, if the probability is 20%, the odds are 20% over 80%, that is 1 to 4. While probabilities go from 0 to 1, odds go from 0 to infinity. Bayes' theorem in odds form shows that posterior odds are a linear function of prior odds with slope equal to the likelihood ratio. So posterior odds are higher, equal, or lower than prior odds if the likelihood ratio is higher, equal, or lower than 1. In the first case, we say that evidence is confirmative, as in our smoke and fire example, where the presence of smoke increases the odds of fire. If the likelihood ratio is 1, i.e. TPR is equal to FPR, evidence is unconfirmative. That is the worthless coin toss evidence that we saw earlier with 50% accuracy. And if the likelihood ratio is lower than 1, the evidence is disconfirmative, i.e. it lowers the posterior odds of the hypothesis. So we can see Bayesian updating as an iterative process, starting with some prior odds. A piece of evidence updates them to posterior odds, which then become the new prior odds. Then a second piece of evidence arrives that updates those odds, and so on. Notice that the updating is multiplicative. This has three consequences. The first is that Bayesian updating is a tug-of-war between confirmative and disconfirmative evidence, which leaves us not with certainties, but with probabilities influenced by priors. That's why people have different beliefs, even if they look at the same evidence. 2, we can converge towards the two boundaries of the probability spectrum, and therefore get rid of prior beliefs, through the accumulation of preponderantly confirmative or preponderantly disconfirmative evidence, even if the evidence is inconclusive. So, for example, we believe that the sun will rise tomorrow, even if there is no conclusive evidence that it will. And 3, a single piece of conclusive evidence, where the likelihood ratio is 0 or infinity, can immediately drive posterior probabilities to one of the two boundaries, irrespective of how much inconclusive evidence has been accumulated until then. That's what keeps conspiracy theorists busy. One last point. In the middle between the two boundaries of faith, where the Bayes rate is either 0 or 1, there is prior indifference, where the Bayes rate is 1/2. You are indifferent about whether the hypothesis is true or false, or is 50%. There is a 50% probability that is true and 50% probability that it is false. Under prior indifference, the Bayes theorem simplifies to TPR divided by TPR plus FPR, which is close to TPR, as typically the two error sizes are not far apart, and therefore the denominator here is close to 1. And actually, in the special case of symmetric evidence, where the two errors are the same, PP, the posterior probability, actually equals the true positive rate exactly, which in turn equals accuracy. In odds form, we say the prior indifference implies that posterior odds equals the likelihood ratio, since the prior odds are equal to 1. This is important because it means that under prior indifference, the probability of H given E is close, or actually equal with symmetric evidence, to its inverse, the probability of E given H. That is correct if the Bayes rate is really 50%. If not, it is a mistake, which is known, among other things, as the inverse fallacy. But more on this another time. Thank you for watching.